That's the equation that you see now on the slide. So we need to find the maximum likelihood estimate, which is find the z that maximizes this. If we take the log of this, this will be equivalent as minimizing the following functional. That functional will be the summation terms high dot exponential, right? So effectively, to maximize the likelihood is the same as minimizing this functional L that you see, minimize it with respect to z. So what I have done on the last equation is rewritten explicitly the summation by multiplying terms together, and you notice there is a quadratic term in z, there is a linear term in z, and there is a constant term. So effectively what we will need is we will need to find the derivatives of this functional with respect to z, so we can come up with a point estimate for the our MLE, the MLE estimate. So so in the next slide I'm going to differentiate the quadratic, will give me a linear term in z, and the linear term in the middle will basically give me the term that you see in brackets on the right side of the equation in the bottom. So let's see how this differentiation will look like. Okay, so here's the same equation that we had before, setting the gradients equal to 0, and there's the answer. We have a matrix A transpose gamma minus 1A times Z, and this comes to be equal to A transpose gamma minus 1 x bar, and x bar is, as you can see from there, it's the sample mean. It's the summation of all my data points xj divided by n. Now you may immediately be able to see that this is the solution you will get with least squares approximation for this problem, but if you want to make it sort of more obvious, you can actually consider only one data point. All right, so we don't have to worry about the sample mean. So if you have only one data point, so only one x, and from it you want to compute the value of z, effectively we will have a functional to minimize that simply looks as x minus z transpose gamma minus 1 x minus az. All right, that's a weighted least squares problem, weighted because there is a gamma minus 1 there weighting the error that you do between the data point x and the approximation az. All right, so this is a weighted least squares problem, and you can write it if you want in a more convenient form by using a matrix decomposition for the matrix gamma, but again the details are in the notes. The conclusion here is that I want you to remember is maximum likelihood estimate is effectively identical with weighted least squares, and the weight here in the approximation is really the inverse of the covariance matrix, so it's gamma minus 1 what comes in the calculation of the MLE estimate. All right, so I want to move a little bit and introduce the concept of additive noise. Of course, we had an additive noise on this example, but I want to sort of do this a little bit more formally, as this case is sort of so popular, you know, in all sort of likelihood calculations, that we need to see this in, if possible, in its general form. All right, so let's wait for the next slide to come, and we will discuss about this additive noise problem. And so effectively what we will do is we will assume that we have some dependence between some data y and some unknown x, that you can think this is a computer code or a function evaluation. So I want you to think of trying to compute x through a model that has the form y equal f of x. Okay, so here is our slide on this topic. So usually when you use either a computer code or some model and you say y equal f of x, and we will see this in the coming equation here, obviously that is an approximation, and the way we account for that approximation is by saying, well, yes, y equal to f of x plus some noise. That's the additive noise there in the model, and we assume some probability model for the noise, typically taken as Gaussian. Okay, so let's consider that the noise probability distribution is given. So the likelihood calculation for this additive noise model is basically the calculation of the probability of y given x. All right. The noise, you can take it that is centered around the origin, around 0. This is very similar to what we had in the previous slides, where, if you remember, we had the noise with mean 0 and a variance gamma, covariance gamma. So the noise, let's say if this is a scalar y and a scalar x, the noise is centered around the origin. So we need to calculate the probability of y given x, and there is the answer on the bottom of the slide. The likelihood basically needs to be evaluated by evaluating the noise model at y minus f of x. So effectively what we do is we take the noise that is around the origin and we shift it around the function f of x without changing basically the noise distribution at all. I mean, this is all effectively what it is in this additive model, and again the distribution for p noise can be anything, but typically with justification from the central limit theorem we take this to be a Gaussian noise. Okay, so here's a plot that shows again the black dots, the data indicating the noise in the data but centered around the origin, and then shifting the whole thing with a function f of x. So think now, how would you write this likelihood p of y given x if, let's say, the noise distribution was a Gaussian? All right. So how are you going to do this when the noise distribution is a Gaussian? How will the probability of y given x look like? And let's take that the noise is a Gaussian centered at 0 with some variance sigma square. Well, there is the answer. So the likelihood model looks as you see on the bottom. You're not going to believe it, but I gave all this lecture with the microphone off. It's Friday. A glass of wine will have turned my brain on, but it's too early in the afternoon, right? One of you needs to be in charge of telling me, is your microphone on? Is this on? Etc., etc. Is your brain working? And usually I realize it because I touch my shirt and it's like, why is this not making any noise? All right. So since I started a new topic, right? So we were talking about this additive noise model where the likelihood is basically like a function calculation plus some noise. And we said that the likelihood, the probability of y given x, is the probability of the noise computed at y minus f of x. So for a Gaussian noise, the way that you see here, the likelihood is basically this nice Gaussian. Okay? And again, in this case, for example, the parameters, of course, are x. But generally speaking, you can assume that sigma squared is also unknown. So when you do maximum likelihood estimate, you can go and calculate sigma squared as well. So you can calculate the parameters of the nodes. Okay.